Thank you very much. First of all, what I need to say is that what was not mentioned in my introduction is that I am a statistician, and that's because I'm not. I did not think about big data. I did not think about how you might deal with data until I was a geologist who finished up with all of this data and had to find something to do with it. So what I'm going to present today is some of my own work and then a whole bunch of other people from CSIRO and from Data 61, which is our data analytics group, around some of the things that you might start to think about in a world with lots of data and how you might make some data-driven decisions in geoscience. So first of all, what is data-driven decision making? When I had the title of this talk, I thought, well, let's ask Google, and you get a whole variety of versions of the different theme, but basically come down to decision making that's backed up by verifiable data. As geologists, we love to measure stuff, whether it be geochemistry, whether it be hyperspectral, whether it be geophysics. We finish up with lots and lots of data at different scales. So the first question, I guess, is what kind of data do you need to make the decision that you need to make? And when do you have enough of it? You can just keep collecting and collecting and collecting and measuring and measuring and measuring. But at some point, you're going to reach a point where you probably have enough to try and make some kind of sensible decision. And then when we have enough of it, how do we find the important things that are in it? So this here was a Goldschmidt abstract from 2016, and there's a few interesting things to take from it. Most of the first paragraph, I think, is very relevant to what we're thinking about. We have highly dimensional data sets in earth sciences that generally have very complex behavior. Uncertainty is a problem. I'll come back to uncertainty a little bit later. And we would hope that we can distill a number of parameters that we can actually track as human beings from these large data sets to target a phenomenon that we're interested in. And we're probably also going to have some Bayesian magic somewhere along the bottom. So I think there's three themes to pull out of this, this abstract. Highly dimensional data, a small number of essential parameters, and some Bayesian magic at some level to try and draw some inferences from these data. So that's the theme I'm going to take from here, looking at some really quite simple ways to try and reduce the dimensionality in big data sets. I'm going to use geochemistry data sets as an example. Talk about an example where we've used hyperspectral data with Bayesian approaches in machine learning to predict some parameters that may be slightly unexpected, and then talk about some data discovery integration in virtual laboratories, some data interoperability ideas. So, reducing the dimensionality. I'm usually working somewhere in an applied geochemistry space, and I often am given a big data set, with 60 elements or something, and said, go forth and find something. And one way of doing this is to do what's called a principal components analysis. Why am I telling you this? Because this is a really simple and useful tool to try and do data mining. And what it does is it takes your data cloud, which if you have 60 elements, varies in 60 different directions at the same time, and I certainly can't cope with about more than 4. I might be able to take 3 dimensions of space and then maybe add time. But in that elemental data set, it's going 60 directions at the same time. And what this kind of analysis does is it just reorientates the data cloud so that you get to see the most variation at one time. And it also quantifies how much variance is summarized on each of the axes in the plot that it gives you back. The other thing that's quite useful is it gives you eigenvectors. So those red lines, they're probably maybe a little fuzzy and hard to read, but in this data cloud, the samples over this end are driven by rubidium and potassium. Samples over the top corner here are titanium, zirconium, bottom corner here, calcium. A really nice way to interrogate, in this case, geochemical data. There are many, many other ways that you could approach this. You could use a self-organizing map or something like that. But the problem with quite a few of the other techniques is that it can be very hard to understand what has driven the groupings or the variance that's being represented back to you. So I'm going to show you two examples where this has been quite effective, and the size of the data sets involved are actually quite small. And that's because I think they're quite elegant examples that we, as people, can actually track and understand what process is being pulled out. And there's absolutely no reason not to apply these these approaches to data sets that have got hundreds of thousands, or even millions of data points in them. So I just want to take a little analogy to try and just help people who are struggling with maybe what this is trying to do. If you imagine your data set as a teapot, there are, you can look at your teapot in different directions. If you look straight on like this, you don't have much of an idea that it has a spout. You don't have an idea that it has a top, and you don't know that there's a handle like this sticking out the back. So what these kind of data analysis approaches are doing are trying to give you an idea what the optimal orientation to view your teapot is, to understand it has a spout, a handle, a knob on the top and a handle on the back. And that's the same kind of idea with the geochemical data set or whatever other kind of data set you're trying to look at. We just want to visualize that data set in the way that is most optimum to see what is going on in it. So here's quite a simple example from Agnew Gold Mine in Western Australia. The pre-existing notion had been that gold was associated with biotite. That was the notion of the geologists on the site. This here represents a portable XRF data set of maybe 200 analyses, where the data points here that have got red circles around them are anomalous in gold. We've got the eigenvectors sitting here, so here's the calcium one that is showing a positive correlation with gold, and potassium and barium are showing a negative correlation to gold. If we want to have a model where, an observation, if you like, where that gold and biotite are associated together, the geochemistry is telling us that that really can't be a relationship that's happening, because potassium and barium, both elements that are likely to be will be incorporated into biotite, have got a negative relationship to these samples. What it turns out is when you start doing some microcharacterization and looking at these samples under an SEM, you find out that the gold is actually associated with a calcic amphibole. The second example I want to show is a data set from the Cloncurry district in northwest Queensland in Australia. And what this here is a whole bunch of ore grade samples from about 27 different deposits in the district. So there's about 57 samples in that data set. And what this is attempting to do is summarize the variability in that whole mineral system in the district. So we're trying to understand in one, oops, that was the forward, I want the laser. In one two-dimensional plot, what the variability of this very complex mineral system is. Up here again, we have the eigenvectors showing you what variability is going on. So coming up this end of the diagram, at the top here, samples are dominated by calcium, sodium, and silica. So that'll be probably albite alteration. Coming over this side here, we're getting iron, copper, cobalt associations. And down this corner here is lead. So this here is an example where we've attempted to reduce the dimensionality of a really complex system using geochemistry and these kind of analyses. Now, why would this be important to you? If you had a whole suite of samples from an area, for example, and you had some really nice mineralized samples, if you had no mineralization, and you were trying to fit some rock chip samples or a new drill hole into an area into this kind of context, you could do this kind of analysis, and you could see where your sample point plotted compared to known mineralization or known anomalism in that area. So again, we're just trying to visualize these large data sets that it can be really complex. Now, another example, the third example I want to touch on here is around using wavelet tessellations to find boundaries, and boundaries of different scales in drill hole data. Now, this can be a really interesting approach. It's something that's been developed by June Hill at CSIRO, And it's about looking at a signal. Ooh, I'm not doing very well at that. This here is a gamma signal. It really doesn't matter what the signal is down a drill hole. And as we come across here, we have different scales. So we start out at a very, meters to tens of meters scale, and then as Tune's indicated here, coming out to a regional scale by the time you get out to these large scale features. And what you can see is that as you start at a small scale and come up, some features persist the whole way through and then disappear, and other features maintain the whole way through. And you can see how, depending on where you set your coefficient index, whether you come in at a smaller scale feature or whether you come in at a much broader scale feature, depends on how many boundaries you see down your drill hole. So this can be a really interesting approach to try and find consistent boundaries in a really big data set, and can be really interesting to help people logging core. Now, the other thing that's quite interesting from this approach is it does give you some idea about gradational boundaries and sharp boundaries. So you see a boundary like this one here that in the signal could be quite gradational. It starts out as being a block of boundaries together as you come up and up and up scale, and then eventually it just becomes a single boundary and then goes away when you get to the very high wavelength of the features. So, rapid resource characterization through analytics. This example I want to explain here explore here as a machine learning approach developed by some of my colleagues and some the guys at Data 61. And what they did is they took a set of representative samples for a mineral system and they characterized them. They got really good data from them, whole rock geochemistry and mineralogy and XRD data and hyperspectral data. And based on these data, they were able to start learning things. And that could be learning from hyperspectral data the geochemistry, or learning from hyperspectral data geometallurgical properties. And then you can start making predictions, you can classify, you can add new samples or new data, and you can look at the uncertainty of these predictions. And if you're unhappy with the uncertainty, well, then that would suggest that you should go back, collect some more samples, and put them in. And the great thing about this approach is that it gives you an idea of what you need to sample or where the optimum sample would be to try and decrease your uncertainty the most. And when you reach the point where you're happy with your uncertainty, your job's done. You can make predictions moving forward. So here is an example from a large deposit in Australia where we've predicted a bunch of things. The first block here is predicting logging code. Now the red bars on here are the prediction, and the black line is truth, what the geologist called the interval. And it's worth noting that the geologists tended to lump a lot more than split. So that's why there are or that would explain a reasonable number of these little deviations away in some of the larger consistent units. That's just the nature of the data. So this is predicted off hyperspectral data, having learned a model based on what the geologist has been calling things. Now as we move across here, the black line is again truth, so that's from chemical analysis. And the blue line, or the two blue lines, or blue envelope rather, is more clearly seen here on sodium. So you've got the uncertainty of a prediction of the different elements in each of those samples. Now, we're predicting off hyperspectral data, so iron and magnesium are likely to be hosted in minerals that are spectrally active, which should make the prediction easy off hyperspectral data. Sodium and potassium and minerals that are probably not so spectrally active, so are a bit harder to predict, and the uncertainty is quite a bit larger. And then finally, what's really interesting is that actually we can predict uranium and copper reasonably effectively, and they are going to be in phases that are entirely non-spectrally active. So the reason we're making the prediction is probably because we're machine learning an association with the other minerals in this deposit that is tied to the uranium and copper contents. So this approach uses cloud-based processing to take really big data sets, to learn a model, to predict the model, to validate the model. And then once you've calculated a model, you can export that model and actually run it on your laptop or a small processor. So you can update your predictions, as new data comes in really easily. And then periodically you have to go back to cloud-based processing to deal with the amount of computational power that's required in these calculations, which are using that Bayesian approach to try and to learn models for these data. You can start to think about the same thing with predicting maps that might help you, collecting features and making predictions. And you can also, the really interesting thing, as I mentioned, we come back to uncertainty. Here is the prediction of a given feature. I think it's going to be iron ore, judging by the fact that Pilbara of West Australia there is lit up. But what's really interesting is it shows you the places where the uncertainty is really high in the model. And that would be places that if you wanted to lower the uncertainty or know more about what's going on over here or up here, that would be a place to go and put some samples in to see if you could get a better model and drive that uncertainty down. So the last thing I just want to touch on for the last few minutes is around data integration and visualization. I'm sure we've all been in the situation where we've gone to a mine site or picked up new ground or picked up another company, and you've got data from that company that doesn't match your database, and you've got a whole bunch of different logging codes and different ways that data's been stored. We're working pretty hard around trying to build spatial information services that can sit over top of different databases and incorporate those data easily. And one thing that is really useful in Australia is a portal called the Ozscope portal, and that sits over top of the different state surveys and the different data that comes in from different states, from different government departments, and it pulls it all together. So you can actually, from a single portal, request all of the data that's held by government at different levels from a single area. And I could visualize a scenario where that is a really useful opportunity for a company to have a similar kind of data infrastructure sitting over top of different assets or different areas where it can all be queried easily. Now, the other thing to touch on when you have all of that data in a single portal is you can start having virtual labs for visualization and to run some of these things. Here's a little virtual lab that we built around using conditional probability to predict things. Over here is one around using geophysics code routinely and making that data processing easier for the user. So virtual laboratories are trying to put the pieces of the puzzle together. You want to get the data, allow the computing to be done, and apply the analytics so that you finish up with extracting the value from that data. And finally, this is kind of trying to get at something of the CSIRO Mineral Resources Discoveries Program's view of how you might have data-driven geoscience. We have industry drivers, we have the Internet of Things, all the cheap sensors that finish up in drill rigs and trucks and all of these places. We just have so much data coming at us. And we want to try and get as much value from that as possible. And then we have the research end of this, where we have new devices, new sensors, the things that we learn, the new research, the intelligence, if you like. And we want to be able to pull those things together, and we're really focused on the goals of exploration through cover and rapid resource characterization. So I'll leave that there, and I'm really keen to pick up on those conversations with people over the next day and a half. Thank you.